Well, so I think we are almost there, so we can already slowly start. So Andrei Parnachev from Trinity College will tell us about the stress tensor sector of conformal correlators and holography.
Okay, thank you. Let me start by thanking the organizers for assembling together this great workshop. I've been enjoying it. And of course, I was really looking forward to coming to the Quarks conference physically, but hopefully that's going to happen. So today I will tell you about the stress tensor sector of conformal correlators. And the main arena here is going to be conformal field theories in d-dimensional spacetimes. So in these CFTs, a 4-point function here depends on the cross ratios or equivalently positions of the operator insertions. You can always use conformal symmetry to put one operator at infinity, one at 1, one at 0, and then the leftover position is what is going to determine the correlator. And the correlator can be written in terms of conformal blocks, these BKs, which are known functions of Z and Z bar. And the coefficients which appear in front is a product of the OP coefficients of operators O1, O1, and OK, and operators O2, O2, and OK. And we are talking about the channel where we take Z and Z bar close to 1. So the OP coefficients are, of course, just the coefficients that appear in the 3-point functions of these operators. And these conformal blocks, they contain the contributions of primary operator OK and all the conformal descendants. Now, another important object in CFTs is the central charge, CT, which appears in the 2-point function of the stress tensors. So if you compute the 2-point function of the stress tensor, there is some index structure which is completely fixed. And then the coefficient which appears in front is the central charge. And in this talk, I will discuss CFTs where the central charge is very, very large. And sometimes I'll also refer to CT as n squared for these reasons. So now in these large n CFTs, major players are so-called double trace operators. So if you have two primary operators O, you can make a double trace operator out of them by roughly inserting a bunch of derivatives in the middle. And for unit normalized operators, the OP coefficients of operators O1 with a double trace operator made out of the same operators scales like 1, and OP coefficients of O1s with O2, O2 scales like 1 over CT. Now, in holographic CFTs, the leading 1 over CT contribution to a 4-point function, or currently the leading 1 over n squared contribution to a 4-point function, receives a contribution from the following written diagram, where we have O1, O1 here, O2, O2 here, and we have a graviton exchange between them. So this diagram, which, as I said, is 1 over n squared, admits a conformal block decomposition. And since there is a graviton exchange, you may think that one term in this conformal block decomposition is just a stress tensor. And indeed, the stress tensor is there. The AP coefficient of operators with T is completely fixed by the word identity and is given by delta over square root of CT. So the stress tensor contributes this for O1 times this for O2. So it indeed contributes something which scales like 1 over n squared. In addition to the stress tensor, there are conformal blocks which correspond to double trace operators, both made out of O1 and O2. And the OP coefficient is actually known. And as I mentioned, this guy scales like 1, this guy scales like 1 over n squared. So the whole contribution is indeed something that scales like 1 over n squared. But in holographic theories, these numbers are also known. Now, one can do the following interesting application of the story. So consider a Fourier transform of this 4-point correlator with 201s and 202s with respect to the positions of the insertions. And consider the regime where the momentum of the Fourier transform, both momenta are very, very large. So this is a Regge regime, which corresponds from the CFT point of view to the situation where both z and z bar go to 1 with the ratio fixed. So it turns out that in this regime, the result exponentiates. What sits in the exponential is so-called the aconal phase, also known as the phase shift. And this phase shift is completely insensitive to the contribution of the double trace operators. So it only knows about the stress tensor exchange. So now, if you consider T mu nu, the stress tensor, as one pair of external operators, the other pair being scalar, and then you impose the positivity of the phase shift, which follows from the entirety of the CFT, you recover a so-called A equals C condition, or equivalently a statement that the dual gravity must be Einstein-Hilbert gravity, and generic high derivative corrections are not allowed. And of course, in gravity, that was derived by Kamacho and Delstein, Multasen, and Zhibayedov by imposing causality of the theory. And then in the CFT language, that was shown to be the case in a number of papers. And technically, the main issue here was decoupling the double trace operators. Now, one can ask a question, what happens if you go beyond the tree-level diagram? What happens if you consider loop diagrams? So some of the loop diagrams appear here and here. And of course, there is also a box diagram, but that contributes to the, appears because of the exponentiation of the aconal phase. Now, generally, all these loop diagrams, and then you can consider high loop diagrams and so on. So what they do is they contribute powers of the ratio of the Schwarzschild radius to the impact parameter to the aconal phase. And there's some interesting physics that happens when your impact parameter is of the order of the Schwarzschild radius. There's some black hole creation. That would be interesting to explore it. But of course, dealing with all these diagrams technically is complicated. Now, the question is, what happens if we make one of these operators heavy? So let's say we keep O1, the conformal dimension of O1 to be order 1, but we make the conformal dimension of O2 to be of the order of CT. And as usual, we take the limit of very, very large CT. Then this diagram actually dies because the coupling to the heavy state by the graviton is enhanced by delta heavy, and this is the only diagram that survives. So this is some kind of interesting regime from the point of view of gravity. Now, from the point of view of the dual ADS theory, this limit that I'm going to discuss in the following, where we take CT to be very, very large, and the ratio delta heavy over CT, which we'll call mu, is fixed, corresponds to a black hole. Why is it so? Well, consider the following ADS Schwarzschild background, where the function f is this, and this quantity mu are the radius of ADS, and this quantity mu is related to the mass of the black hole in this way. Now we use the usual ADS CFT dictionary, which tells us that the conformal dimension is proportional to the mass, and the ratio of the radius d minus 1 over g Newton is the central charge, and recover our formula that this mu, the fixed, the finite number in the description of the ADS Schwarzschild black hole, is just the ratio of the conformal dimension to central charge. So to summarize, the limit of large CT with mu fixed is a black hole. Now, what is the CFT language description of this limit? So in the CFT language, the stress tensor contribution becomes something proportional to two OP coefficients. The heavy operator OP coefficients is this, light operator OP coefficients is this. So in our limit, the stress tensor scales like mu. The double stress tensor scales like delta heavy squared over CT, delta light squared over CT, so it gives us mu squared. There are many double stress tensors. And then the K stress tensor contributes mu to the K. So we will be interested in the contribution of all these K stress operators, which we call the stress tensor sector of the correlator. Note that in 2 dimensions, It's known exactly. It goes under the name tensor vacuum block, the identity, and that has been explicitly computed thanks to the existence of tensor symmetry. In high dimensions, the situation is more non-trivial. But before we get into this, you may ask, okay, so what if we know the stress tensor sector? What about other operators? For example, in free theories, in weakly coupled theories, there are lots of light operators which can contribute. Then there are double trace operators, which I just discussed. And the answer is, and I hope I'll convince you, that the stress tensor sector is kind of special. Once your theory becomes more strongly coupled, the light operators mostly decouple. And the double trace operators, you can also decouple by either taking the limit delta large much larger than 1, but of course keeping it much smaller in CT, or considering some observables. One of these observables I already mentioned, the econal phase, which is sensitive to double traces. So in the rest of my talk, I will mostly discuss the situation where these multi-stress tensor operators will be taken at the leading twist. So this is some special subset of multi-stress operators, which is interesting for reasons that I'll try to explain. And this leading twist multi-stress tensor contribution can be reproduced in holography in certain limit exactly. And then I'll briefly discuss the story beyond the leading twist. So let's start with the setup. So the setup is that we're considering correlator on cylinder. There are two heavy operators inserted at plus infinity and minus infinity, and two light operators whose position on the cylinder differs by delta t, delta phi. So this is one light operator, this is another light operator, and you can compute the cross ratios z and z bar, and they're related to delta t and delta phi in this way. So one can think of this correlator as a 2-point function of light operators, expectation value in the heavy state created by heavy. So the stress tensor exchange, so let's consider what is the conformal block decomposition of this correlator in the heavy light channel. So the stress tensor exchange, as we discussed, produces order mu term, which is completely fixed by word identity, and the twist of the stress tensor, which is the spin minus the conformal dimension, is d minus 2, which is the minimal twist, because stress tensor is a conserved current. Now, at order mu squared, so there's just one operator at order mu, but at order mu squared, there's suddenly a whole bunch of them, infinite number of them. And one can consider leading twist operators, where a twist is 2 times d minus 2, where just insert a bunch of derivatives in the middle of stress tensors. And then you can start contracting indices that decreases the twist. You can start contracting more indices that decreases the twist even further. So at each twist, you have an infinite number of operators, and there is a whole family here. So note that order, as I said already, contribution at mu k comes from k stress tensors. So the leading twist of these guys has twist k times d minus 2. Now, to compute the whole stress tensor sector, you need to know all these APs coefficients, all the big coefficients, and that's kind of hard. So let's simplify our life a little bit by taking the Litecoin limit. Z bar goes to 1. So as well known, Litecoin OP is dominated by operators with a leading twist, with a minimal twist. Well, this is very easy to see. Consider an OP of 2 scalar operators. There's this term, and then let's say we have an operator with spin L here. It needs to contract x's with indices, and Litecoin limit means that x mu is finite, so all these guys are finite, but x squared goes to 0. So this means that the leading contribution comes from operators with the smallest twist tau. And this is reflected in the near Litecoin behavior of the conformal blocks. So the near Litecoin behavior, as z bar goes to 1, behaves like 1 minus z bar to the power k d minus 2 over 2 for leading twist operators, t to the k. So these are operators that I'm going to look at. And they're interesting for a variety of reasons. So in particular, it's an interesting fact that their big coefficients exhibit some universality, Namely, they're not affected by higher order gravitational terms in the bulk in holographic theories. They're completely fixed. So can keep all of these leading to its contributions by keeping the parameter mu tilde, which is mu times 1 minus z bar over t minus 2 fixed. So in the following, I'm going to take this double scaling limit where I send z bar to 1, send mu to infinity, and keep mu tilde fixed. This will keep all leading twist operators. And it's basically the closest analog to the Brasseur vacuum block that we have in high dimensions. Now, it turns out that you can compute all these guys by using bootstrap and certain ansatz. Let me give you a flavor how it works. First of all, the order mu tilde contribution is just a stress tensor, so it's completely fixed. It's the Litecoin limit, near Litecoin limit of the stress tensor conformal block, where f is some hypergeometric function. And then the key point is to make an educated guess for order mu tilde squared, mu cube squared, and so on. And the guess is that to order mu tilde squared, we have, this is the whole thing. This is a product, each term has a product of two f's. And the sum of subscripts in f sum to 6 in this particular case. So for mu tilde cube, it's a product of three f's. And the sum of the subscripts sums to 9, and so on. So there's a reason why we ended up with this guess. It's not proven, but it works. So one can then bootstrap, and bootstrap, actually you see that the kind of equations that you get is an overcomplete system of equations, but this ansatz, which is what we call it, solves all of them. And we can solve for these coefficients order by order. So in particular, if you start with the stress tensor, the stress tensor term at order mu tilde has some polynomial, some series in z, and some series in z times log. And from these numbers, you can read off the OPE coefficients and the anomalous dimensions in the cross channel, where you fuse the heavy and light operators together. And well, the cross channel, of course, it produces the same result. So you read off the OPE coefficients and the anomalous dimensions. And then the OPE coefficients and the anomalous dimensions completely determine all terms which contain log squared at order mu tilde squared. So this determines all coefficients in the ansatz at order mu tilde squared, and this is the result. So, and then you can continue and get the whole correlator, heavy, light correlator this way. Now, this result, of course, you can also use to read off the OPE coefficients of multi-stress tensor operators. So in particular, the product of the two OPE coefficients is given by this formula, where all these guys are known. And from here, you can also read off the OPE coefficients of light operators with the double stress tensor. And it's this OPE coefficient. Note that, as I mentioned before, at large delta, it indeed scales like delta squared over CT. Now, as I said, you can compute our correlator in the double scaling limit to any order in mu tilde. We can read off the OPE coefficients to leading order in 1 over CT. We recover this way the OPE coefficients which have been computed using holography. And we also observe that the correlator exponentiates in the sense that this function f has a finite limit as delta light sent to infinity. The correlator further simplifies if, in addition, you take a large volume limit by sending the radius of the sphere to infinity, and then the result is an expansion of powers of mu times delta x minus delta x plus cube. And these are the first few terms in expansion that have been computed using the bootstrap. Now, it turns out that you can do a simple holographic computation which reproduces this bootstrap result and gives you even more. And this is just a statement that in holography, heavy, light correlator for large delta, you can compute by just computing the length of a geodesic which connects the 2 points separated by delta t and delta phi on the boundary. However, since you want to compute the contribution of the leading twist correlators, you need to do some rescaling. So it's not quite the Schwarzschild background. Schwarzschild background, this calculation is complicated, but you can do a rescaling of the coordinates by keeping this coordinate fixed and this coordinate fixed, and considering the mu goes to infinity limit, which is what you're supposed to do when you take the double scaling limit. So the resulting metric has this interesting form. It's fairly simple, and you can compute. Compute geodesics by doing the standard exercise where you have two Killing vectors, two conserved quantities. You write down the geodesic equation this way, and then you need to find the length. So all of this is standard. The only problem is you have to regularize. But this you can do, and the result is something that is written in terms of this kind of elliptic integrals. So in particular, if you specify d equals 2, then you recover the Virasoro vacuum block. The Virasoro vacuum block, as I said, has been computed before and naturally recovered. Things only depend on delta x plus there, not surprisingly. So in d equals 4, you get a new result. You get the new result as the expansion in powers of mu delta x minus delta x plus cube, which is the same as the expansion in powers of temperature to the fourth delta x minus delta x plus cube, which is of course exactly what you expect for near Litecoin correlator. So for generic correlator, there would be t to the fourth times some combination of delta x minus delta x plus, so that the sum of powers is equal to 4. But since you're specifying the near Litecoin one, that's the only thing you can get. And these are the first few terms in expansion, which indeed reproduce the bootstrap result, and of course give you infinitely many more, much easier. So this is actually the whole result, the whole resummed function that you can write down. So this is holography. Now, you can ask a question. Can you go beyond the leading twist? So far, I just discussed the situation at the leading twist. And the answer is yes, you can actually take the bootstrap and go beyond the leading twist. But you will need some extra data. In particular, since beyond the leading twist, the OP coefficients are not completely fixed. So for example, depending on which holographic theory you have, which high derivative terms you have, you may get different results. So you need some extra data, but the bootstrap still works. Another thing that happens beyond the leading twist is that you can connect the results to a different computation, the computation of the phase shift or the econal phase delta, which in the heavy light limit is particularly nice because you can compute it to all others in the ratio of the Schwarzschild radius to the impact parameter radius. Remember I mentioned that if you have a light scattering, it's an interesting question how to see how the black hole is formed. Well, here, if the black hole is there, this computation is actually easy. We have done it, and you can observe how when the impact parameter goes below the photosphere radius, that is your state is being eaten by the black hole, the phase shift suddenly develops a large imaginary part, which of course corresponds to the inelastic scattering. So your cross section is precisely the geometric section of the black hole in this limit. And so what's interesting is that you can connect the phase shift in gravity, which is known exactly, to the CFT data that you compute via bootstrap, and the two things match very nicely. And then you can ask, okay, so all of this is very nice, but what happens if you go beyond gravitational holography? What happens if you have a finite gap in the system? It turns out that there are finite gap corrections to the OP coefficients. And that is true even for the leading twist OP coefficients. And so you may ask, okay, so is the stress tensor sector still special in any way? So let me give you one example, which I believe still demonstrates that stress tensor sector is special. And that is the example of large N CFTs at finite temperature. So in all large N CFTs at finite temperature, the stress tensor sector thermalizes. In other words, the one-point function of the stress tensor in the heavy state is exactly equal to the thermal one-point function and temperature beta, where beta is determined by the following equation, by the saddle point equation. And this follows from two facts. This follows from the equivalence between microcanonical and canonical descriptions. That follows from large N. And in addition, you need to use the Eigenstate normalization hypothesis. And that follows from the fact that this is basically the OP coefficient of the stress tensor with O's, and this guy is completely fixed by the word identity. Now, large N factorization in large N CFTs implies that the finite temperature expectation value of T to the K operator is just the stress tensor operator expectation value to the power K, which scales like delta heavy to the K, and then there's some number depending on what kind of contractions you have here. Therefore, thermalization of the K stress tensor, so if the same statement is true for the K stress tensor, is equivalent to the statement that the VEV, the TK in the heavy state is the same as delta heavy to the K times some number, which depends again on the contractions. And this is actually a statement about the OP coefficients of the multi-stress tensors. So now it doesn't follow from the word identity anymore. However, you can check it because this is precisely what we've been discussing so far. So this is a statement about the leading delta behavior of multi-stress tensor OP coefficients. You can check it. And indeed, it works. And it works, well, it works in holographic theories, but that's not surprising. Even if you add some high derivative terms, it works. Not necessarily for leading twist operators. This is not surprising. But it also works for free field theories. For example, for the kind of theories that Bo was talking about. So it would work there as well. So then we conclude that the multi-stress tensors do thermalize in large N CFTs, which is not necessarily true for generic operators. Okay, so now let me summarize. So what did I tell you about? I showed how we can compute the heavy, light correlators to all order in the parameter mu using the bootstrap. And then I computed it in the large delta light limit using holography, and there is a perfect agreement between the two sides. And then I also mentioned one application beyond the leading twist. So all of this was in the leading twist. I also mentioned one application beyond the leading twist where we observed that the stress tensor sector thermalizes, even in non-holographic large N CFTs. And here's the to-do list. What are the things that I think are interesting? So first of all, there is this formula. No, I showed you a formula in terms of some of the peak integrals for the heavy, light correlator. And okay, it's a closed formula, but it's kind of, I'm still hoping that there is something nicer, it simplifies in some way, because it's so simple for the D equals 2 case. And a related question is there some symmetry behind the Litecoin correlator? So in 2 dimensions, this Virasoro vacuum block appears and so nice because of the Virasoro symmetry. And there is a lot of, by now, some hints which tell us that there is some kind of symmetry which governs the near Litecoin limit of correlators in high dimensional CFTs. And this is related to, well, for example, the leading mu term in the expansion of heavy light correlator is exactly the same as the leading mu expansion in the heavy light correlator in the 2-dimensional theory, which has a W3 algebra. And indeed, recently there were some papers which studied the algebra of generalized ANEC operators, and they do have a kind of central extension which the W3 algebra has. So the leading term, so it's very much like W3 algebra. And in fact, if you go beyond this and compute the heavy light correlator and W3 algebra to next order, what you observe is that it satisfies the ansatz that I've been talking about. But the numbers that appear in the result are different from the numbers that appear for the heavy light correlator in D equals 4. So the hope is that it's some kind of W algebra maybe that is behind all of this. And of course, in 4 dimensions, it would be W3. In 6 dimensions, it would be W4, and so on. Next thing that I would like to do is to understand thermal strongly coupled large N CFTs using this technology. And I think it's actually quite promising because, well, as you know, there are lots of questions you can ask in thermal strongly coupled large N CFTs using holography. Like some of these things that come to mind are transport coefficients, and for example, pole skipping versus chaos relation. And all of these things are very nice, but it would be, I think, helpful to understand them from the purely CFT point of view. And finally, I still think that all of this is going to say something interesting about this Regge limit of scattering and gravity where you form a black hole. Thank you very much.
Thank you, Andrei, for this very nice talk. Are there some questions? So Bo is cheering at least. Yes, so Grisha.
Yes. Andrei, thanks for nice talk. I have 2 questions. At some moment in the middle of the talk, you have shown heavy light correlator. And if I'm not mistaken, your expression had some poles for dimensional light operator being 2. Could you comment on this?
Yeah, very good question. So what happens when what happens there is the mixing. So when your when the dimension of your operator is integer, then the multi-trace operator made out of all light has the same conformal dimension as the multi-stress tensor operator.
So you're talking about level crossing?
Yeah, they have exactly conformal dimension, the same conformal dimensions. So what happens is a mixing, and what happens is both of them has the same kind of poles, but let's say so both of them have the same poles, and then the poles cancel, and then you get some block terms. So that's basically what happens.
And if I'm allowed, just second short question. At some moment when you go to this double Litecoin limit of the correlator, you have shown formula which had some log x plus delta x plus delta x minus. Yeah.
This.
Yes.
Oh, this is boring. This is just the.
No, there was a previous one. Previously there was a similar formula. Maybe. Yes, this one.
Oh, it's the same. It's just the zero temperature result. It's just the correlator to operate the pure CFT piece.
Why this law comes with coefficient which just doesn't depend on anything?
Yeah, because the zero temperature result, it's the OO computed at zero temperature. So it's just 1 over x, 1 over delta x minus delta x plus to the power of delta. So all of this is supposed to be multiplied by delta light. So that's all. That's the meaning of the story.
Thank you very much.
Okay, thank you. So there are still 2 questions, but so I propose that we do these 2 questions and then we kind of officially start the general discussion session so that people can ask people to the 3 speakers for this afternoon. But now Bo and then Mihailo.
Hey, thanks for a very nice talk. Of course, I'm intrigued by your to-do list. But also you gave some, you know, in the actual content of the talk, there's information that is useful for that to do, right? The Regge limit and, you know, maybe creation of black holes from two particle scattering. Can you summarize in some way where this heads? It's really intriguing.
Yeah. Well, okay. So I don't really know how much we can say about the create. No, the short answer is that this is, of course, precisely a question that we'd like to investigate. But unfortunately, I don't know how much, like what kind of useful stuff we'll be able to say about this light scattering situation. But you know, some physics will presumably be the same. For example, as I mentioned, when you do the heavy light scattering, at some point this delta, the anomalous dimension, becomes imaginary. Now, so generally, there is a relation between the anomalous dimension and, sorry, the delta is a phase shift. So generally, there is a relation between the phase shift in the heavy light channel, in the cross channel, and the anomalous dimension of the heavy light operators. So let's say we have a 1, a 1, a 2, a 2, and a 2 is light. So there's a relation between delta and the anomalous dimensions of operators which appear in the cross channel. And when it becomes imaginary, then one interpretation is that the anomalous dimensions in this channel become imaginary. So then it's natural to say that, well, maybe in the light case, what happens is also the anomalous dimensions of this type of operators become imaginary. So that's you know, some interesting physics that would be interesting to you know, to explore more. And another kind of question that you may ask on this, no, it's not directly. Well, it's sort of slightly further away from this black hole creation limit, but still, like, there is this universe. Well, so when the particle falls into a black hole and approaches the photosphere, there is some kind of universal behavior of the phase shift. Because, you know, what happens is you lower your input parameter, it gets to some critical value, and then spends a lot of time, and then maybe it goes away. There's some critical behavior of the phase shift in this regime, and that is related to some behavior, some asymptotic behavior of the OP coefficients of the multi-stress tensors. So that's also an interesting question, how like critical behavior in gravity is translated in some kind of universal behavior of the OP coefficient. So yeah, so there are all sorts of interesting questions that one may ask.
Thanks a lot. There was, you could say much more than I expected on this. So that's great. Thank you.
So Mihailo Chubovic.
So I'm also intrigued by the to-do list, but the previous point. So as you said, you now have the framework to understand from field theory viewpoint the thermal physics and quantum chaos. So in particular, you already know how to compute the phase shift delta in diagonal approximation. So can you say something already? Would you expect maximal chaos for these operators?
Well, that's actually an interesting question. So first of all, let me remind you that maximal chaos, I mean, of course, the best, I must say I'm a bit confused about maximal chaos, because the sort of cleanest, well, so one way to view maximal chaos is to consider correlators in the Rindler space, which usually serves as a good description of finite temperature physics. And then the chaos regime corresponds to considering the correlators in the Regge limit. And the correlators in the Regge limit, you can map, no, the good thing about the Rindler space, you can map it to the flat space. And I mean, sorry. So you can map it to the hyperbolic space at the temperature, which is of the order of the curvature of the hyperbolic space.
Mm-hmm.
So, and the chaos regime is the Regge limit of the correlator. In other words, you can probe the you can probe the chaos regime in the finite temperature hyperbolic space situation by just looking at the graviton exchange in the 4-point function. And of course, you get the usual chaos behavior. This is what the original paper did on chaos, the bound on chaos paper. That's what they did. And now you can also consider the 2-point function of the stress tensors in this regime. And you happily observe that butterfly velocity, the pole skipping, the parameters that you get from the pole skipping agree with the parameters that you get from the chaos bound. So, in other words, everything is completely, here, all calculation is completely fixed by the stress tensor exchange. And there's basically nothing else to do. Now, when you ask a question, basically this is what you're asking, right? When you're asking about the chaos bound, how does the pole skipping and the...
Yeah, so it works the usual way, basically.
Yeah, so this is basically it as far as the situation on the hyperbolic space is concerned. Now you might ask a question: what happens in the flat space? Of course, not hyperbolic space, the flat space. And there, of course, you have infinitely many graviton exchange. The multi-stress tensors. So that's where all these multi-stress tensors come into play. So yeah, so in principle, it would be interesting. So I guess the answer is yes. In principle, it would be interesting to answer this question: what happens if you have a flat space at finite temperature, and presumably all these multi-stress tensors contribute now, and there still has to be this correspondence, as we know from holography, between the out of order correlators, which give you the Lyapunov exponent, and the pole skipping, the TT correlators, from where you can read the pole skipping. Yeah. So yes, I would say from this technology you should be able to get this just from conformal field theory. Yeah, that would be, I suppose, that would be an interesting exercise.
Yeah.
Then there are, of course, questions so this would be one thing, and the other thing would be, as you know, the bound on the ratio of the entropy to shear viscosity is violated in high derivative gravities, and if you're allowed to throw in various high derivative terms, you can get all sorts of numbers. So one natural question is, are there some the kind of CFT technology may give you a much better formula, may give you much better control on the transport coefficient formulas than gravity in a way. So that's another direction I think is promising.
Thanks.
You. So yeah, so as I suggested, we can officially start the discussion session. So if people have any question to the three speakers of this afternoon,